And the reason to write it like that is because if you remember the cosine function can be expanded into two exponentials. The cosine of x is e to the ix, right, plus e to the minus ix divided by 2. So this is how you define the cosine function. So if I have this term, I can backward translate it back into cosine function. And you can see the emergence of the periodicity, right? The cosine, of course, is periodic, right? So this is all I have to do. So this is just to show that this function is a periodic function if you define it this way. And again, why I show this? Well, because you can verify that this is a periodic function. How? Well, because by adding a periodicity. So if you put in x to evaluate this u of x, right, you get some term. And then if you add a periodicity, right, to the function to the periodicity that you have, this guy here, x plus a is my periodicity period between my atoms, then these two functions should be identical. Okay? And you can try this out on using this periodic function, and you can verify that they are the same. Right? If you add a periodicity, you would not see any difference in this. Okay, so it's the same deal, right? So here you have, instead of you have different region of space, you now have periodicity for your potential curve. Potential have periodicity, and then you solve for this equation of state, the differential equation, kinetic energy term, potential energy term, total energy, right? So this is my my potential energy term, and you add this. You simply substitute this function into here. And after a little bit of math, okay, so I will skip all that. If you trust me on this, then you will see that the solution is simply a sum over some constant, the c constant, e to the minus I g dot x, right? G is my residual space vector, and then the wave function, plane wave, e to the I g dot r. So you get back. So you define these whole functions for the periodic function. You can test it. How do you test it? Well, you test it by doing this, right? By changing x with the periodicity and make sure they are the same. So you do it this way, you get back this plot function, this u of k of x times a plane wave. Okay? That's what you have. Okay. So what I like to hopefully partially convince that you have this. If you have periodic potential, you get a plane waves, right, weighted by a periodic function. So this whole thing is called a graph function. And so what to do next? Well, once you got this function, you can substitute back into here, right, into my equation of motion equation here, my Schrödinger equation, and solve for the energy. It's a rather involved process, so I won't do it. You can solve it by matrices. Some of you may or may not have matrices. But the idea is that if you do that, what you got is that you got multiple solution. You have multiple solution for your energy, and this leads to multiple band structure because you have multiple solutions. So just like in the double square well case, whereby your energy, each energy level of the single square is split into two. Here, in the periodicity, you split into many states because of the periodicity that you have. Okay, so that's about it. So that's basically what I want to tell you about mathematics-wise. So I promise won't use so much more math after this. And so we have. If you go back to this picture that we see, so here we have a periodic functions, right? So here we got, try to explain this with the picture instead. So if you start off with this functions, right? So this is my periodic function in one direction in the x direction. In the x direction. So this is my, what are these well look like? Think of these as hydrogen atoms, right? Or helium atoms, some atom, and you will see this well, and this well is 1 over r, right? Follow 1 over r, the Coulomb potential, of course, right? This is 1 over r, and deep down, and 1 over r potential in mathematics is very hard to solve potential because it's so-called non-local, because it can blow up at you when r is equal to 0, right? So this is a tricky potential to solve, in fact. And so this little point identified the location of my core atoms. So if you can think of it deep down below, these are location of my nucleus. So of course this is the periodicity, right, between them. Define my periodicity of my lattice. Okay. So what I found, if you solve for this Broadway, what you think is that for one of the wave function, what you got is a wave that represents the solid line. Okay, so this wave give me a lower energy state. Okay, so that's why you have accumulation in the well region. So they give me a lower energy state. So give me one energy for this well. And then the dashed line, so in between these potential, correspond to a higher energy state, right? So this is a splitting, so you can think of this, I have two energy levels, right? One is the low energy state, I have accumulation of charge or a state, a wave function inside my well, whereas the other one, I have in between in the barrier, at the barrier, between the well, right? And this one has a higher energy, total energy that I found. And you can see that I have this periodicity along with my wave functions, right, which is what I expect because I have a periodic function. I should not see any difference. I would not be able to see any difference if I'm here or here because they would all look all the same to me because of this periodicity effects. And because of this splitting, so here I plot down here I plot a functions, right? Here, what am I plotting? I'm plotting k vector, right? My k vector, and energy on this side. Okay. So in the case of free electrons, what is the energy dependent on this? Let me just show you this. This is kind of useful to remember. If I go way back to my free energy case, this notes here, you got energy is proportional to k squared. So you plot E as a function of k, what do you have? Right? E as a function of k, you get a parabola like this, right? So that's what you see. For free electron, you get a parabola like this. And so, and that's exactly what I have. I have here, this is the free electron case where I would get a parabola. Now, if you impose the periodic function into here, I would then starting to split my energy level like this. At each of these points, this is a point, I'm going to split my energy level into two. So I have two possibilities. One is going this way, which is inside trapped like this. The other is in the barrier, right, between them. So I split it into like this. Okay? So you are starting to see, instead of parabola, you're starting to see gap in between. And these gap, of course, will lead to the band structure. These are the band gap that you see in between different energy levels as you go through. Okay? So now you can plot this parabola in a different way. So let me show you how people plot these things. Because here you're talking about K space now, right? In residual space, K space, residual space. You can plot it. Remember in K space, we are thinking of the K space. Of course, is also periodic. You can define Brillouin sum